Okay, so we left off with the negative exponent rule. Can I get everybody's books up here? Okay, so we were looking for an example of the negative exponent rule. So if we had, for example, if we had something like x to the negative 2, what's that going to give us? 1 over x squared, okay. If I had something like 1 over x to the negative 3, what's that equal to? X to the third. So our short way of remembering that is a negative exponent in one part of the fraction. When I say part of the fraction, I mean numerator or denominator. So a negative exponent in one part of the fraction becomes a positive exponent in the other part of the fraction.
So how would it be if it was in the numerator?
Say it again.
How would it look like if it was in the
Well, right there. That's the numerator, right? Because it's over 1. Okay. Zero exponent rule. What's that tell us? A, with A as a number, to the 0 power, what's it equal to?
0.
No?
It equals 1.
Equals 1. So anything taken to the 0 power is always equal to 1, except 0 itself. That's indeterminate. 0 to the 0 could be anything. Yeah.
Why is it equal 1?
Okay, so that's a good question. Let me think of a way to do that one. It's a good question. Okay, I think here's maybe the best way to do it.
Did he just stun you?
Okay, here's how we can do it. Let's make a list of powers of 2. It's really, you ever get Kale's question?
Yeah.
Why does the 0 exponent rule work? Here's probably the best way I can think of to explain this. So if I take 2 to the 1, what does that equal? 2. What's 2 squared?
4.
What's 2 cubed?
6.
8.
2 to the 4th?
16.
Okay, let's do 2 to the negative 1. What's that? 1/2. Okay. 2 to the negative 2.
1/4.
Etc. Right? So we could have this list go on and on and on. So then this should work. What does 2 to the 0 have to be if I follow that trend?
1.
Everybody see that?
Wait.
Right? Because aren't I just, when I move down the list, aren't I just multiplying the previous result by 2 every time?
Yeah.
1/4 times 2 is 1/2. 1/2 times 2 is 1.
So
1 times 2 is 2.
So you're saying it's like dividing.
So if you go down the line, it's divided, right?
If I go up the line, it's dividing.
Yeah.
Right? Yep. Either way, okay? Or multiplying by 1/2, either way. Okay. So that's why, I mean, there's I could maybe prove this a different way, but you wouldn't like it as much. Does that one make sense?
Yeah.
Wait,
So it's always 1? So no matter like what it is?
Doesn't matter.
8 trillion.
Because those didn't have to be 2s, did they? Those could have been 3s, in which case I would have had 3, 9, 27, etc., right? 1/3, 1/27, and in that case I would have been multiplying by 3 if I went down the line. But it doesn't matter, no matter what, that's always going to be a 1.
Wait, what if it's 1?
What?
So then you already have 1.
What's 1 times 1, Jim? Never mind. That's no.
Okay, but you can see why it doesn't work with 0, can't you?
Yeah.
Right. Everybody saw it. I mean, 1, you get why 1 would be 1.
Yeah.
Okay, but you see why, and this is, we just can't do, I mean, none of this would work because you can't take, well, what if we try to do it with zeros? So we get 0 to the 1 is what?
0.
0. 0 to the 2 is
0.
0. 0 to the minus 1 is undefined, right? Because you can't divide by 0. See what I'm saying? So it's not really going to work with zeros. It's not really going to work with zeros. Because we can't even, we can't even go this direction. So what do we do? What do we do to get from there to there? Anything. There's nothing specific. Right? I could multiply by anything to get from 0 to 0, couldn't I?
Yeah.
Right? You see why it's indeterminate? Okay? So we don't know what this would be. 0 to the 0 equals, who knows? Because what did I do to get from that term to that term to that term? Right? See what I'm saying?
Yeah.
Okay. All right. Okay, so an example, I mean, this is kind of a dumb example, but any number, I could take the number negative 14 to the 0 is what? 1. What about x to the 0?
1.
Is 1 as long as x doesn't equal what?
0.
0. All right, so moving on. Let's just practice these a little bit. And let's actually do some of these. We don't have to do them all, but I want to do some of these. This is, and that your first assignment is just going to be a bunch of stuff like this, right? A bunch of just solving fairly complicated expressions, simplifying complicated expressions using properties of exponents. So let's do number 2. How about?
Negative 16.
What do I have to do? There's a bunch of properties that are being. Okay, good. If I'm going to simplify this, I have to do exponents before I multiply, don't I? Right, I'm going to follow PEMDAS. So the first thing I would have to do is take care of that exponent. Well, what's the property we're using there? Did that one? We did that one, right? Oh, you know what? We didn't even do that one. That one doesn't show up on here. Oh, yeah, it does. Never mind. No, it didn't.
Oh, wait.
Nope. It's a combination. We have to do a different rule.
You add them?
So let's do.
Would it be 2 times 9?
So there's another rule that they didn't even give us that we have to add. Okay, here it is. And we know this one. What is this rule? If I take, I don't think we did this one, did we? Is that on the other page? I don't think so. If I do a product to a power, what's that equal to?
Oh, it's,
A times B.
A to the m times b to the m. Okay, right? Now, I want to, this is, even in an honors class, this is a common one. People overgeneralize this rule. Here's what can happen. Now, why is this the case? Let's look at a proof of this real quick. Wouldn't you agree that a times b to the m is just equal to a times b times a times b? How many times? M times, right? So multiplication is commutative and associative. So I could reorder that product of factors in any way I wanted to. Is there a convenient way I could maybe reorganize that chain of factors?
alphabetically.
Okay, why not just do this? Why not make that a times a times a, how many times? M times. Times b times b times b, how many times? Okay, so then what is that? Times b to the m, right? Make sense? Okay? Okay, so now what I want you to not do though, and this is when I say overgeneralize, it means, okay, if that's true, then maybe this is true too. Is a plus b to the m equal to a to the m times, or plus b to the m? It's not, right? It's not. Yeah, because that's saying something very different, right? That's like saying if I do a plus b to the m, what is that? A plus b taken to the m power, that quantity, boy, that's something very different, right? That's gonna equal A plus B times A plus B how many times? Okay, that's a horrible mess, isn't it?
Yeah.
Right, because if we're gonna simplify that, every time I multiply an A plus B times an A plus B, for example, I've gotta FOIL that out, don't I? Right, so this first one, this would give me A squared plus 2AB plus B squared. Then I've gotta multiply that times another A plus B and FOIL it all out and get something even nastier. And then I gotta take that and multiply it by the next one. So you can see that the pattern is this just gets bigger and bigger and uglier as m gets bigger, right? It's not as simple as just saying a to the m plus b to the m. There's a whole bunch of other terms in there that I'm neglecting, right? So I'm gonna put a big fat slash through that, meaning it is not true. Don't make that mistake, okay? So then let's go ahead and prove, now we can be smart about this and we don't have to do anything like this here to get this answer. But what about if I wanted to do A over B to the M? We know what the answer is, right? What is it? A to the M over B to the M. How could I prove that? I mean, I could do it this way, right? I could write it as A over B times A over B times A over B. That's fine. I could do that, right? Everybody gets that. We could do something like this.
But that's stupid.
How many times am I multiplying those?
Yeah.
M. Okay, so then I could simplify this by just multiplying straight across all the numerators, right? So I'm getting A times M times over B times B times B M times. Isn't that just A to the M over B to the M?
Yes.
Okay. Another way we could do it. How could I do it without invoking some kind of a sequence like that? Could I just use properties of exponents that we already know?
Wait, shouldn't it be the same fraction anyways? If you're not multiplying that fraction by any other fraction, shouldn't it be the same fractions?
What do you mean?
Power?
That's a tongue twister.
What do you mean by that? I'm not
So
following.
like, you multiply A by the same number as you multiply B's and it's still the same fraction, just written larger?
But they're to different powers,
Oh,
right? Like what, I'll give you an example. 2/3 squared is not 2/3. 2/3, what is it?
well, it's based on this number.
2/3 squared would be 2 squared over 3 squared, right? So it'd be 4/9.
Oh, yeah,
See what I'm saying?
that makes sense.
Okay. All right, so what about this one then? What if could we use some properties of exponents to get here? So A over B to the M. What could I do inside the parentheses? Let's not work outside, because let's pretend we don't know this. We're trying to prove this relationship, right? So what could I do inside? Go ahead. 8 times 1 over B, okay. What is 1 over B? If I use my properties of exponents we just reviewed, 1 over B to the 1 would be B to the negative 1, right? A positive exponent on the bottom becomes a negative exponent on the top, agreed? Okay, so another way we could do this, we could say something like A times B to the minus 1 to the M, right? Everybody agree? Okay. So we already proved this relationship, didn't we? Okay, so if I'm taking the product of A times B to the negative 1 to the M, we said that a product to a power equals the product of the powers, right? Let me say that backwards. I said it backwards. A power of a product equals the product of the powers. right? If I'm taking a power of a product, I can write that as the product of the separate powers. That's what we just proved. So if I apply that logic to this down here, what am I gonna get? A to the m times b to the negative 1 to the m. Well, what's b to the negative 1 to the m? Ah, good. If I take a power to a power, I multiply the exponents, right? So that gives me a to the m times b to the minus m. And a negative exponent on the top equals, aha. Okay, we just proved it. Either way, we get the relationship though, don't we? So we got that one, and we got this one. Some new ones we added. Okay, so now let's try number 2. And how about if I take, I'm gonna make that bigger, so we have more room. So what do I do first? Okay, so I've got a product to a power, right? Power of a product. So what can I do? As long as the things in here are being multiplied, what did we effectively do over here when we applied this property? I mean, it's almost like we distributed, right? We didn't technically distribute, but it's almost like we distributed the power to each of the factors. We can think of it that way, right? As long as they're being multiplied, I know I'm gonna get each one of those separately to the m power. So let's do that here, right? Can't I kind of distribute this to? How many things am I distributing it to?
2, 2, 3, 4.
And yeah, boy, I'm getting lots of different answers. They're all, you could make an argument they're all right, but there's one best answer here. I'm gonna say 3. What are the things it's being distributed to? Negative 2, okay, good, so we're gonna distribute it to the negative 2, to the a cubed, and the b, right? So this part right here is gonna become negative 2 squared times a cubed squared times b squared, right? What's negative 2 squared? 4. A cubed squared is a to the 6, and then I get a b squared, right? Okay, times 8ab to the 9th. Still, right? We've still got this piece over there. Did I have to show all those steps? No, probably not. You can do that in your head, right? We just know that I can jump right to the 4 because I'm squaring the negative 2. I can jump right to the 6 because I'm taking a power to a power. And I can jump right to the 2. Okay. Now what? Kind of, when you say that, combining like terms is something that we would use to describe what happens when we're adding up a bunch of terms, like terms. So I think you're thinking the right thing, but I want you to say it more precisely.
It says combine like terms, isn't it?
Yeah, adding.
Yeah.
It says that in the solution?
No, it says.
In the notes.
Oh, in the notes?
But when it
That's, I think,
it says when adding or.
when adding or subtracting. Right. So we know, and we'll look at some examples like that. But here I'm not really combining like terms. I'm using some properties of real numbers that we talked about at the beginning of the year. And we throw these words around a lot. Multiplication is commutative and associative. Let's remind ourselves for a second what that means. What's it mean that multiplication is commutative? I can rearrange factors in any order I want to, right? Associative means I can group them however I want to when I'm multiplying a bunch of things together. Okay? So why not, let's go ahead and do something like this. Why don't we let's rearrange these. So we're gonna commute them, so we're gonna take the product of the integers first, right? So what's 8 times 4? 32. Okay, let's commute them, so we're gonna multiply the a factors next. What's a to the 6th times a? A to the 7th, because there's an invisible 1 there, right? So I get a to the 7th, and then finally I've got the b's. What's b squared times b to the 9th? So there's my answer. Okay. Now here is an unbelievably good hint for you. This, you gotta take this one to the bank. This is one you can use a lot. How would I check to see if I got that right? And this, you can do this like on SAT tests.
Teach me.
How could I check this? Give A and B a random value and evaluate up here, and if I get the same number I get when I evaluate here.
So kind of like when we check our answers on decimal system, like we set an equation, and then we make the values A equal 1, B equal 2 kind of thing.
Well, like what if we, here, I'm just gonna, I wanna demonstrate this to you, just so you can see how great this is. So what if we pick, like, let's just pick random values for A and B. So let's pick something like, how about A, boy, we don't wanna pick too big a numbers, because they're gonna be huge here.
1, choose 1.
So A could be, oh, it's gonna be huge.
Said 2.
Make BB 1.
So if A is 3 and B is 2, what's gonna happen here?
Not too big.
So I'm gonna get, if I plug those in up here, I'm gonna get -2. So let's look at this guy up here. I'm gonna get, just wanna show you this good trick. So this is gonna give me, if I plug in, what were those values again?
3 and 2.
3 and 2. Okay.
3.
So if I plug in 3 for A, what's 3 cubed?
8. Wait, 3. 27.
27. B is 2, so I get 54 times -2 is -108 squared. Right, so this is all gonna give me 108 squared times, you get big numbers. 8 times A, that's 24, right? Times 2 to the 9th is gonna be 512. So I get 108 squared times 24 times 512.
Yeah, show us this whole.
Oh, hang on, I did that wrong. It's gonna be, no, that's right, 512, right? So I could multiply that on a calculator and get a number. Okay, what about down here? If I evaluate this one, I'm gonna get 32 times A to the 7th. Okay, how could I do A to the 7th? A to the 7th is gonna be A cubed, which is 27, times A cubed, right, which is 27. So I could do a 27 squared, and then I got an extra 3, right?
Oh, yeah.
Times B to the 11th. Well, if B to the 9th is 512, you guys can tell me pretty quickly what B to the 11th is. Good check. That's it, 2048. Okay, oh, you just double it twice, right? If I multiply it by 2 and then multiply by 2, 2 powers of 2 would mean I'm doubling it twice. So we'd have to just show that those two things are the same, okay? And would they be? They would be. But we did it right. If you had access to a Desmos scientific calculator on, say, like the SBAC test, or which you probably will, and I think they're going to start doing it on SATs here in the near future too. So here's another way you could do this one. You could go the Desmo, well, not the graphing one you won't typically, but a lot of times you'll have an embedded scientific calculator maybe, for example, right? So you could do something like this on Desmos. Okay, all you'd have to do Okay, if I wanted to do scientific calculator, all I'd have to do is something like this. I could do, now watch this, this is pretty cool. I could do f of a and b is equal to that, right? This thing right here.
And then we just put it in the equation.
Yeah. Okay, and then I could just come down here and go f of, what I pick, 3 and 2?
Oh, I thought the
Oh, it's
second-
ninth, whoops. Big number, right? But then I could just come down here and take my answer.
Could we also just say A, B equals? Like, in separate lines? Like A equals next line, B equals?
Maybe. I can't, yeah, I think you could. Let's try it. Well, here, I'll try it down here. If,
Yeah.
okay. I don't think you can. Oh, maybe you can. So A
Yeah, A
equals 3, B equals 2. No, it doesn't do it.
I think, don't you have to do it with the F?
Oh, yeah, yeah. Still doesn't do it. Still doesn't do it.
So it has to be like function form?
Yeah. Yeah, it has to be like that. Now what it do? There we go. Okay. So then I could do like G of AB
What does G stand for?
equals my answer, right? So 32 times A to the 7th times B to the 11th. Hey, Jim, quit talking. You guys quit talking back there. So then I got G of 3, 2, right? Same thing. So I know I did it right. Okay? That's a pretty good trick. It's a really easy way to check to see if, like, if it's a big, hard problem. It's a pretty easy way to check to see if you got it right. Okay?
Is that on the test?
I mean, yeah, if there's an embedded calculator, you can, and typically I do. So, yeah. Okay, going back, let's try another one.
Wait, so what was number 2 next?
What? Say it again.
Okay.
Okay, let's try.
Yeah, can we work on number 3, please?
Yeah, we can do a better one than that. Okay, yeah, actually, that's a good one. Let's do that one. Let's do number 3. I didn't actually know that last one was going to work. I'm glad it did. But I wasn't sure you could do F in Desmos, you could do a function of multiple variables, but that's a good way to do it.
And G is just another way to say it, right? We don't want to
Yeah. Yeah, just so I had different functions on there.
Okay.
Okay, so what do I do here?
This is for divided fraction.
Yeah, I'm just going to follow PEMDAS.
So don't we do our variables for divide to equal divide?
Okay, I got divide before I add, right? Okay. So then this first term, now look what I can do here. I can take advantage of the fact that I've got like bases. I've got m. When I say a base, you know what I mean, right? When we're talking about a power, if I do something like a to the m, that whole thing is called a power, right? This is the exponent. This is the base. And the whole thing is what we call a power, right? Okay, so I've got like bases here. I've got a 54 over 3. That's easy to simplify. What's 54 over 3? Okay, so this part right here becomes an 18 on the top, right? Okay, what about if I divide these like bases? Let's take this part.
Would it be 4?
Okay, so that's the same as m to the 4, right?
Yeah.
M to the 6 minus 2. And then how about this one? N cubed. So I have 18 m to the 4th n cubed minus 10 m to the 4th n cubed. So I get 8 what? Okay, right, so then if I'm, so somebody explain that. What's-
Right, you subtract the exponent in the m part, so when you subtract 4 from 4, and that would leave you with just add it to 0, which is equal to 1.
So, okay, so here's the question. The question is, do I subtract the 4s here?
No, I don't think so.
I don't.
It's
I
because
don't.
it's subtraction, right?
Okay, and here's how you can remember this. Well, I have 18 of something here. What do I have 18 of? M to the 4th n cubes. Whatever that is, I've got 18 of those. That's all a coefficient means. I've got 18 of those minus 10 of those same things, right? Okay, what is m to the 4th times n cubed? I don't know, something complicated, but it's a thing that I've got 18 of, right? So 18 of those minus 10 of those is 8 of those. Okay? See how that works? Okay, now hypothetically, what if we had gotten, when we were doing this problem, what if we had gotten something like this instead? What if I had gotten 18 m to the 4th n cubed minus 10 m to the 4th?
Then you can't do anything.
Can't do anything. You're right, because they're not like terms.
Oh,
I've got 18 of these, 18 apples minus 10 oranges, they don't subtract, right? They're not like terms. Okay? So, okay, we did that. Good. So, how about, let's look at another important one.
Number 5, maybe?
Number 5 is probably a good one.
That's another one.
Okay, let's do number 5. That's probably a good one.
That or 8.
We'll do more than one. These are probably good to go through. Oops. Okay, what am I doing first? Does everyone take a second and study this?
PEMDAS.
I'm just doing PEMDAS, right?
The exponent.
Gotta do the exponents first. Good, so step 1, and if we go down, let's just write out PEMDAS. So the first thing we do is exponent, right? So that means I've got to deal with this guy. Well, I've got a product of stuff. Nothing's being added or subtracted. So I can distribute that to the factors that are being multiplied or divided, right? So where do I distribute that? I'm going to distribute it to the 2/3, which is really the same thing as distributing it to the 2 and the 3, right? I'm distributing it to the r squared, and I'm distributing it to the s to the 7th. Okay, so what do we get from step number 1 then? 4 ninths r to the 4th, s to the 14th. Good. Okay. Times 1/6 r cubed s. So now, what do I do here? Okay, I mean, kind of, not really technically like terms, but we're going to multiply in a convenient order, right? We'll multiply the fractions first. So 4 ninths times 1/6 would be 4 54ths, which can be reduced. Oops, 4. So what is that? 2/27. after we reduce. Okay, we get r to the 4th times r cubed is r to the 7th, good. And then finally I get s to the 14th times s. There we go. Okay? Make sense? Okay. Let's do, okay, how about number 6 is a pretty good one too. There's something there that we can do. I know I'm spending kind of a lot of time on this, but I think you're going to thank me for taking a little extra time on this.
Was it just flipped upside down?
Yes.
Basically. That's good. Good idea.
Okay. What about here? What are we going to do?
Distribute the exponent.
Okay, no. Let's follow, we're going to follow PEMDAS. There's something we can do first.
14
Jim
divided
Caleb,
by
up
7.
here, please. What could I do? Yeah, in fact, I always want to work inside parentheses first, right? So inside the parentheses, there's some stuff I can do.
Would that be 2 over?
So inside the parentheses, 14 over 7 reduces to 2. Okay, so I'm getting a 2. And w to the 12th over w cubed is w to the 9th. Okay. Now, what can I do with this whole thing?
Make it into a fraction.
Yeah, well, I can, you're right. So I got another question along the way this comes up. What if I have something like a over b to the negative m?
I ain't doing
You flip it.
There you
No,
go.
wouldn't you just
I
flip
could
it?
write that, anytime I have a fraction to a negative exponent, I could flip it to the positive exponent. Everybody see that trick?
Yeah.
Right? Because this is going positive on the bottom and that's coming positive on the top, right? I mean, you could do it in another order. I could distribute the negative m and then do that individually, but that's more work. Right, so all I've got to do here, this fraction is over 1 to the negative 1 would equal the fraction 1 over 2w to the 9th to the 1. And anything, I don't need to, just to the 1, I don't need to have that 1 there, do I? Yes, sir.
Would it be, or is that a -9 like 1 over 2 W?
No, it wouldn't be, because there's 2 ways to get here. I could flip the whole thing to the positive 1, which would be the easiest way, and then I don't even need the 1 there anymore, do I? Right, then that's equal to just 1 over 2 w to the 9th. The other way you could do this is, what if I did distribute that? You'll see this is harder. That's going to give me 2 to the negative 1 times w to the negative 9, right? Well, doesn't that mean the 2 goes to the bottom and see what I'm saying? Either way,
Is it
I'm
kinda
getting
like
that,
we
but
did
this is
with
easier.
I? Is it kind of like we did with I, like you just put the I instead, but in this case we just make it a fraction? Like, you know what I mean?
Didn't follow that.
So like if it's like -10, we use I, but in this case it's like a -1 exponent, we just make it a fraction.
Well, if it's a negative 1 exponent, we're using
Yeah.
this property, that I'm just the negative exponent property is all we're using. Okay, and then finally, let's do, okay, I think number 7, and then I think we're good.
Does this list them?
Okay, what about this one? What would I do? This isn't very hard. What would we do? So yeah, I could reduce the fraction, right? 15 over 24 reduces to 5 over 8. Okay, so I'm going to get 5 over 8. And then what about if I look at this?
We'll do the same thing.
Okay, that's x to the 10th divided by x to the 12th is what? x to the negative 2, but a negative on top becomes positive on the bottom. This is why I showed you that little trick yesterday. We go back to our list. Remember this little trick. If I have a to the m divided by a to the n, it's equal to a to the m minus n, but what if n's bigger? If the bottom exponent is bigger, here's the rule. We could leave the base on the bottom and subtract the top from the bottom and just do it in one step, right? So here, let's apply that thinking. So here we've got x to the 12th and x to the 10th. Well, 12 is bigger than 10, so we'll leave the x on the bottom and we'll subtract 10 from 12 and get x squared. And just do it in one step. Okay? What about the y's then? Good, I'm just going to get y to the 4 minus 3, which is y to the 1, so that's my final answer.
Whoa, wicked.
Okay? Make sense?
That does make sense.
Okay. All right, so we'll just add a couple little notes, and I think we're out here at 10, is that right?
Yeah.
Okay, so we don't have much time, but we'll at least just fill in a couple of blanks on this stuff. So polynomials. Let's just talk about what a polynomial means. So a polynomial is a sum or difference of many monomials. Poly means many, right? The highest exponent of a polynomial is called the degree. The highest exponent of a polynomial is always called the degree. Standard form for a polynomial means we always want to write with the exponents in decreasing order. So for example, what would, there's a couple other things that they just kind of glossed over that I want to maybe point out too. So if we're writing a monomial, what are the characteristics of a monomial? If we're talking, a polynomial is a bunch of a sum or difference of a bunch of monomials. If we take an individual monomial, an individual monomial could be written in the form a times x to the n. So what has to be true of n? Anybody know? Well, you could even have multiple variables. We're not going to deal with that. We're going to deal with polynomials of a single variable, because almost always we do. But what about the exponent? What kinds of numbers could the exponent be? That's what I'm asking. Say it again. It could be 0, but it can't be negative, and they have to be integers also. So it has to be a whole number, right? So there's two things that have to be true. One, n is a whole number, and then what about a? The only thing that's going to be true for a is not very restrictive. I know we're not used to seeing weird numbers in front of weird coefficients. But they could be. It could be pi, it could be the square root of 2. It just has to be a real number. Okay, we'll pick up there tomorrow.